Okay, today we are happy to have Charan Cheng from UIUC. Charan is a fourth year PhD at UIUC, advised by Ge Liu. He's working on the theories of generative modeling and AI for science. And now it's up to you.
Thanks. Thanks, Tony. Thanks for the great introduction and thanks for having me. So today I will introduce our recently accepted work on Riemannian consistency model. So as its title indicates, we're mainly focused on two topics. One is Riemannian manifolds. The second one is consistency model. So it's probably getting a bit like theoretical in the later slides, which we will like dive into in our talk. So feel free to interrupt me or post a comment or question in chat channel if you want. So let's get started. Well, I will first start with the common diffusion and flow matching as a general model, which I believe everyone here is probably pretty familiar with. So as a quick recap, the diffusion is a generally random process that iteratively refines the noisy data into clean data. And the flow matching can be thought of as a continuous time generalization of diffusion, which allows for a more flexible design of the probability path, like the OT path. So both diffusion and flow matching requires a decent number of steps for decent generations, usually ranging between 100 to 1,000. This is because the marginal score or the vector field is not necessarily straight. So we need to follow this kind of integration of the vector field produced by the model in order to achieve decent results. So the consistency model was just proposed to address the sampling efficiency issue with the diffusion and flow matching models. So instead of like learning the vector field itself, the consistency model maps any points on the ODE trajectory directly to its original data. So by any points, I mean arbitrary noisy data on the probability flow. It can be like having any arbitrary level of noise like this by varying the t from 0 to 1. In this case, it's 0 for capital T. So on all of the examples, we hope that our model can learn to map these data into our clean data X0. So by the way, there are two different conventions, namely the diffusion convention and flow matching convention. So for the rest of the slides, I will use the flow matching convention because we mainly follow the Riemannian flow matching. In that way, we treat t equals to 0 as a noise and t equals to 1 as the clean data. So the core idea behind the consistency model is that on these generation trajectory like these, the prediction should always be consistent. Like the f of arbitrary xt t should be always x1, in which x1 represent the clean data. So in this way, with a consistency prediction, we can shortcut the probability flow in order to achieve few step generations while maintaining its generation quality. So the consistency model was already like proposed in Yang Song's seminal work in 2023. However, at that time, it was only applied to like Euclidean space. So let's get into more details of the original consistency model for Euclidean space like image pixels. There are two core components for consistency model, namely the consistency parameterization and the consistency loss. So the consistency parameterization is more like some kind of like boundary conditions in order to force the model to learn meaningful things, which is like if we plug t equals to 1, we obtain that the model's prediction on the clean data x1 should always be x1 itself. So these poses a constraint that we cannot use arbitrary unconstrained denoiser as our small f. Instead, the original paper, the authors proposed to use a linear interpolation between the unconstrained denoiser and the data points. So you can verify by yourself that when t is equal to 1, the contribution of the unconstrained denoiser just vanishes. So we can fully recover the clean data of x1 itself. So these kind of like serve as the boundary condition for the consistency models that prevents a model from collapsing into trivial solutions like the model always output results like 0. So this is always consistent, but this is meaningless. We do not obtain any useful information from the data itself. So we want to avoid these. Well, the second components, I would say, is more straightforward. So in order to enforce the consistency constraint, we hope that the distance between the two predicted data points on the same marginal path should be as small as possible. So we just like penalize these consistency loss by measuring their distance, square distance. So in the original paper, we just like use a pre-trained flow matching as the marginal vector field. We take a one-step ODE to obtain like adjacent points on the same marginal path, and then we make two different predictions, and we say like their prediction should be as small as possible, the distance. So for Euclidean data, we always like use the MSE, which is the Euclidean distance, as the loss to penalize the consistency, which I guess kind of makes sense. So with these two key components in mind, we now try to like extend them to Riemannian manifolds. So we want to extend these two core components to Riemannian manifolds. Like, for example, the geographic data on the two sphere, as demonstrated on the right, we may have like torsion angles, which lies in the tori, which means that they have like periodic boundary conditions. We also have like rotation, like the protein backbone rotation, which lies in the manifold, Riemannian manifold of SO3, the special orthogonal group in 3 dimension. However, I want to note here there are two major challenges of like simply adapting the Euclidean cases to Riemannian manifolds. Namely, first of all, the Euclidean consistency model parameterization may break the manifold constraint, which means that simply like linear interpolation between the prediction and the data itself may leave the manifold. This is because the manifold may be curved, so the linear interpolation may not arrive at a point that is meaningful on the manifold. What's more, the Euclidean CM loss is ill-defined for Riemannian manifolds. For the same reason, we cannot like simply subtract the 2 points on the Riemannian manifold, which does not mean anything. And probably the MSE is not a well-defined metric for these terms. So in order to extend consistency model to Riemannian manifold, we need to address these challenges. So this is what our Riemannian consistency model tries to do, which is the very first grounded attempts to extend consistency model to Riemannian manifolds. We summarize our contributions as follows. So first of all, we address the first Riemannian parameterization problem by ensuring the Riemannian constraint by design. And furthermore, in later slides, we'll demonstrate our Riemannian consistency model support both distillation, namely RCD, as well as training, namely RCT. We also provide an intuitive interpretation from a physical, or more specifically, a kinematic perspective to intuitively understand like how our Riemannian consistency model can work. So probably we should get into the details. You can also like see the right figure as a direct demonstration of how our Riemannian consistency model can work. So as mentioned before, in order to address the first core challenges in extending consistency model, we do not use simple linear interpolation between 2 points. Instead, we use some kind of like Riemannian flow matching parameterization on the Riemannian manifolds, in which we rely on the exponential map to ensure the manifold constraint. Of course, as the same case for Riemannian flow matching, we also have the scheduler, which defines the speed you want to travel along the geodesic. So in most of the cases, the kappa t is simply like 1 minus t, which demonstrates the remaining time we try to travel. And also we parameterize the vector field instead of like a points on the manifold itself. So for the RCM loss, a similar spirit just apply. The only thing different is that we use the Riemannian distance or the geodesic distance instead of the MSE. So the geodesic distance can be understood, at least in most cases, the shortest distance on the Riemannian manifold. So which can safely replace the Euclidean MSE in our losses. So yeah, let's get into the roadmap of how we derive these. So according to the previous slides, our loss is actually the so-called discrete time RCM loss, which means that we still requires choosing a discretization, namely these n and delta t, in order to like make a small approximation on the marginal pass. So we demonstrate that we can extend them to continuous time losses, in which we just take the limit and rely on some core components in mathematics to derive the loss. We then demonstrate that with our marginalization theorem, we can extend the distillation to twin, in which we do not rely on any prior twin per twin diffusion of Lemaitre model. So after that, we propose the approximation proposition, in which we propose a simpler RCT or RCD loss, which can like accelerate the training time. So let's get started into the first components, which is probably the most important one in understanding our work, which is we try to go from discrete to continuous time. So the problem with the discretization is that, well, it's always not like numerical stable, as demonstrated in a new paper, the SCM, the simplifying consistency model. So in the original consistency model, the delta t need to be carefully chosen in order to balance the numerical issue with the performance. So instead of like relying on this discretization, we consider like infinitesimal change or instantaneous change of the consistency parameterization. Intuitively, as demonstrated on the right figure, we require this kind of like change to be as small as possible. So I'll just skip the details in the theorem proof, but I will mention two important concepts here, which is covariant derivative and differentials of the exponential map. Specifically, the covariant derivative describe how the vector field changes on the manifold, and the differentials of the exponential map describe how the target changes with respect to small perturbation in the exponential map. We'll get into details into these two components, which is actually the core idea behind our Riemannian consistency model. To understand this, we need to start, we better start with the Euclidean case, which is like familiar to all of us. So let's consider an alternative parameterization for the Euclidean case, in which we have the f of xt, t equals to xt plus kappa tv. So instead of like linear interpolation, we just like travel, we just predict the vector field and travel for the rest of the time. So by taking the time derivative on both sides, we obtain that the time derivative of our Riemannian of our consistency parameterization is equal to three different terms. The first two terms, I guess, is pretty understandable. The important thing is that it turns out to have an additional vector field derivative term, which sums up to like the time derivative of our consistency parameterization. So in order to calculate the vector field derivative, we cannot like directly differentiate on manifolds because of the following two reasons. The first and the most important is that, well, the tangent space at the different points are different. So you can see these at the right figures. If we just move a small bit along the geodesic, this will also lead to like a different planes of tangent spaces. So we can just we just cannot like directly subtract the two vectors because they are lying in different vector spaces, and this is not meaningful. So we must define a way to like compare these two vectors in two different tangent spaces and try to differentiate them. The second problem is that the local geometry might be anisotropic, meaning that, well, the Euclidean space just look like everything like the same across all directions, which might not be the case for a Riemannian manifolds. It might be like curved in some direction, but curved out in some other direction, like the saddle surface. So we need to capture these geometric characteristics in our Riemannian consistency model. So the mathematicians just derived or invented the concept of covariant derivative, also known as the affine connection, to allow us to differentiate the vector fields like on Riemannian manifolds. So intuitively speaking, the covariant derivative generalizes the idea of directional derivative in the Euclidean space and allows us to differentiate a vector field even they are at different tangent spaces. So with these, we can like safely say that we can differentiate even a vector field on the Riemannian manifold along some geodesic. So there are two arguments of the covariant derivative. The first is can be understood as the curve in which we try to like differentiate the vector field, and the second argument is just the vector field we try to differentiate. So I'll skip the details, but I will mention two important like results from the covariant derivative. So when the first formula is met, this covariant derivative is zero. We say that V is somewhat constant along the V, so along the geodesic gamma. So this is similar to an idea in Euclidean space in which if we have the time derivative is equal to zero, we say that the vector field is just constant. So in this case, we say the vector field V is parallel transported along the curve gamma. And what's more important is that when the gamma itself leads to a covariant derivative of zero, we say the gamma is autoparallel, or in other sense, the gamma is a geodesic. So if you recall, like the Riemannian flow matching relies heavily on geodesics in order to like define probability paths. So the covariant derivative is the core components in this way. So I'll pause for a while as this is probably too much math. Any questions so far? Cool. Yeah, let's continue. So yeah, basically, if you look at like our results back, our loss, it contains like covariant derivative terms in order to capture the geometry of the Riemannian manifolds. So after we have like converting the discrete time to continuous time, we now move to our second goal, which is we try to go from distillation to training. So this is to say, like, can we rely on conditional vector field instead of like marginal vector fields? This is because like the marginal vector field is intractable from data itself. And in practice, we must rely on some pre-trained Riemannian flow matching model to approximate the marginal vector field, which may have some approximation errors, of course. So on the other hand, the conditional vector fields are known to have closed form solution and can be easily calculated in this way. So we naturally want to like utilize the conditional vector field instead of like the marginal one. So it turns out that in our theorem 3.2, which is the marginalization theorem, we also demonstrate that this can be done. Basically, which means that we can just use the conditional vector field instead of like the marginal one while achieving the same results, assuming a perfectly trained model. So in this theorem, as is the case for the previous consistency model by Yang Song, we know that the subgradient is required for proof. However, on the other hand, for distillation, as is also the case for in the Euclidean consistency model, the subgradient is not necessary. So our proof rely on the linear property of the covariant derivative with respect to its first argument. So our proof is fundamentally different from Song's original CM proof. Yep, I'll just skip the details, but if you're interested, feel free to check our paper. So here's our last goal. We try to go from complex to simple, which is we try to get rid of the differential of the exponential map. This is because, at least in our case, these differentials needs to be implemented symbolically. which means that in some cases it does not work with the PyTorch's like building autogram. Here's one example why it does not work. So say if we want to calculate, we want to differentiate on SO3, the rotation group. So basically we know that, well, the rotation can be represented with a 3D rotation matrix, which is a 3 by 3 matrix. However, in most of the cases, our tangent vector is just a 3-dimensional like vector. So this is the shape mismatch that we cannot use JVP to calculate in our like in with the autogram. We must like implement deduce some symbolic relation between them in order to implement these. So that is to say, like we want to get rid of like this complex symbolic calculation. So the proposition 3.1, our approximation proposition, just resolve this issue, which basically just says like instead of like relying on the final prediction of f theta, we instead relying on the prediction of the vector field. So in this way, you can see like the derivative of the vector field can be reduced to only 3 terms, which only relies on the covariant derivative, but not the differentials of the exponential map. So in this way, this kind of like simplified laws can like replace the original laws if you do not know or do not want to calculate these kind of differentials. So importantly, these approximation just holds perfectly if like in one case, if the differential map is the exponential map is symmetric, like the Euclidean or the torus cases. In the second case, if the vector field is parallel to the true marginal, these approximation also perfectly holds. So in practice, we observe that these approximation often work pretty well so that their performance is pretty similar to the original one. So let's summarize our contributions in our Riemannian consistency model. So we propose 2 variants, each with their simplified loss version. So the RCD can distill or pre-train Riemannian generated models, and the RCT offers a standalone generated framework which you can train from scratch without like a pre-trained model. So we also demonstrate the algorithm, which you can see like it's pretty simple and similar. You can just calculate everything, either relying on a pre-trained model or just train from scratch. So I guess that's all about the theoretical parts. For the next section, I will talk about our intuition and our physical inspiration from the for the Riemannian consistency model. Any questions so far? Well, if no, I'll just continue. So, as mentioned in the very first slides, we for the first time propose a kinematic perspective for interpreting our Riemannian consistency model. So let's first consider like uniform circular motion on the unit sphere. So we know, although the circular motion is called uniform, or in other sense, the velocity is uniform, the acceleration is non-zero. This is because we're traveling along a curved space instead of like a flat Euclidean space. The centripetal acceleration satisfies this kinematic equation. So the plus sign here just means that the direction of the acceleration is pointing towards the center of the origin. So the kinematic equation describes how a point moves on a curved spaces. Similarly, with flow matching, we are actually moving the probability mass across a curved manifold. So they must also confine with these kinematic or physical principles. So indeed, in this case, the kinematic equation just like coincides with the geodesic equation. They are completely the same, which means that for non-flat Riemannian manifolds, there exists an extrinsic acceleration due to the manifold constraint or due to the manifold curvature. if the manifold is non-flat, it has non-flat curvature, either positive or negative, will inevitably have this kind of like additional acceleration. So this kind of acceleration is measured by a mathematical components known as the Christoffel symbols, which just describe the local geometry of the manifolds. So you may notice there are three scripts of the Christoffel symbols. They actually correspond to the different directions we try to like differentiate. So this also resolve the issue I mentioned before, that is the Riemannian manifold may be anisotropic. So the Christoffel symbols just capture the differences in their different directions. So with these in mind, we now can provide a kinematic perspective for the RCM laws. We know that the RCM laws can be decomposed into three components. The first two components, which might seem familiar to you because they also appear in Euclidean cases. The first one is the learning error, of course. So we hope that the learning error should be as small as possible. The second is the derivative of the vector field, the time derivative, which means that the vector field should remain constant if the manifold is flat. However, we know that since they are non-flat Riemannian manifolds that has extrinsic acceleration that is imposed to the vector field, we now consider like the third components of the covariant derivative, which is exclusive for non-flat Riemannian manifolds. So with all of these three components, we can establish a complete kinematic perspective for our consistency model on Riemannian manifolds. So I guess that's all about the theoretical part so far. Well, we can finally get into some experimental results I want to show you. So we just like we first like categorize our models into three categories. The first one is of course the Riemannian flow matching. We test with 100 steps, which is often the SOTA. We also like test with the two-step Riemannian flow matching, which often generates like results that is not meaningful. We just separate the distillation models from the training models. And importantly, we tested with the Euclidean consistency model with two steps. That is, we just totally ignore the manifold constraint and treat them as if they are embedded in some Euclidean spaces, which kind of still work, but I will demonstrate in later slides. They just for sure compare with our Riemannian consistency model family, in which our manifold constraint is guaranteed by design. So in the first case, we just like test our model on the two-sphere, the geographic data. So for both distillation and training, you can see the RCM variance just consistently achieve better generation quality in the two-step generation setup. Specifically, if you look at closely at the RFM2 baseline, you will see that the points is just too scattered because the original Riemannian flow matching is not designed to handle few step generation setup. However, our like distillation baseline can indeed capture these kind of like few step generation, specifically the two-step generation setup. So as the negative likelihood calculation is not available for consistency model, we usually rely on external matrix. For example, we first calculate the manifold kernel density estimated densities, and then calculate the empirical scale divergence between the ground truth data and our generated data. On the other manifolds, we rely on the so-called maximum mean discrepancy or MMD on manifolds with a modified geodesic kernels to measure the discrepancy between our generations and the ground truth data set. So you can see that for the most of the cases, the simplified laws achieve comparable results with the original laws. And what was more important, the naive Euclidean baseline just quickly falls short. So these demonstrate we need to like respect the manifold constraint when we try to do general modeling on the Riemannian manifolds. So here's more like generation results. So on the upper figure, we have the generations on the SO3. in which we just demonstrate how the 3 points, the original axis frame, are rotated by some like data points. So you can see, like, although the Riemannian flow matching with 100 steps achieved pretty decent results, its two-step variance just like fails completely. However, after distillation with our Riemannian consistency model, it can recover the original results with the two-step generation setup. The same is for like the torus data sets demonstrated before, which demonstrate some kind of periodicity along the boundary. We also like investigate into the impact of number of function evaluation. That is the number of sampling steps in our Riemannian consistency model. So what is interesting is that we found out that, well, the Riemannian flow matching model, for the Riemannian flow matching model, increasing the NFEs has a significant impact on the generation quality, which I guess kind of makes sense because we know that uh, their learned vector field is not necessarily straight. However, it turns out that the RCD and RCT generations are more stable with respect to NFEs, consistently achieving decent generation quality. So this is also like echoes with the results of the so-called consistency trajectory model, in which they also demonstrate, like, for consistency model, increasing the NFEs does not necessarily improve the performance. And importantly, we know that the two curves just intersect at around like 20 steps. So before, like below 20 steps, the consistency model just excels comparing with the flow matching model. We also tested with the scalability with respect to the manifold dimension. So in this case, we generate high dimensional tori data with the standard Gaussian at each corner. So you can expect that there are exponentially many constraints in order to, like, at each corner, there should be consistent number of points. So you can see, like, the naive Euclidean consistent model just quickly fails to capture these exponentially many constraints. However, our RCT or RCM variance is guaranteed to respect the manifold constraint by design. So there's no issue. It can capture the constraints pretty well. So that's all about the original paper. However, currently I would like to demonstrate some additional results we're currently working on. So we're working on the scalability of our Riemannian consistency model to real-world applications, namely the protein generation. So for those who are not familiar with the protein generation, so our base model is called the frame flow. So it's a flow-based generated model by learning the rotation and translation of each amino acid. So it operates on the special Euclidean group of SE3, which is composed of SO3, the rotation, and T3 of translation. So they often require at least 100 steps for decent generation results. So you can, as demonstrated on the right figure. So we just used our Riemannian consistency model framework to distill a pre-trained frame flow in order to enable few step generation. And indeed, we're able to achieve some pretty decent results. So this figure just demonstrate some kind of like proof of concept results for either of the rotation or translation. So in these experiments, we just fix one modality and generate the other. So you can see, like, we generate 10 predictions from the marginal paths and observe their consistency behavior. So each of the data here are actually 10 different generations at different time steps. And you can see they are pretty consistent in terms of their positions and also in terms of like their atom positions due to different rotations. So in this way, we're confident to say that at least for this one modality generation, one-step generation already achieved decent results with our Riemannian consistency model. So we then proceed to like complete training of like a combination of two modality, both of the rotation and translation. And it turns out that we can achieve some more reasonable structure in the full step generation setup. For example, the free flow with 5-step generations just like fails to capture the important like secondary structure like the alpha helix and beta sheets in protein. However, our distilled model can effectively capture this kind of like features. However, we notice that at a cost, the diversity just degenerates. Like there are few beta sheets and more alpha helix in this way. So we're still working on this, and we hope to like achieve better results and hope to inspire future work. So in the last slides, I would like to talk about one specific limitation of our Riemannian consistency model. So for all consistency models, the likelihood calculation and even the elbow is not available. This is because of the exact likelihood which was proposed for flow matching models relies on the determinant of the inverse Jacobian as the change of probability terms in the push forward. So for common normalizing flow, this is achieved by restricting the model architecture so we can obtain a closed form solution for each layer. However, for continuous normalizing flow, this is as the flow is always locally reversible, we can just like integrate the trace of the Jacobian instead of like do the numerical inverse of the Jacobian. However, in consistency model, this approximation is no longer available. This is because we're moving at a very large step. For example, we just like have 2 steps, so we need to leave 0.5 in the time steps. So we cannot say like the determinant of the inverse Jacobian. It's just like the point at this prediction that is inversed. So there are large gaps. So we cannot like calculate the likelihood rely on these methods. And furthermore, I think there's no work that has established the elbow for the few step generation for consistency model. However, we should rely on like external metrics like KL divergence or MID as demonstrated in our work. I think it's also a pretty interesting directions for exploring consistency model in the future work. Yeah, I guess that's all about my talk. Thanks very much. And if you have any question, I'd be happy to answer them.
Thanks for the talk. Does anyone have any questions? Or maybe I would go first. So my question is, so I'm curious about like how many efforts there would be if extending this framework to like a Riemannian flow, a Riemannian mean flow.
That's a very good question. So I would say it's easy because we're already implementing it, but not in our work because we think like the extension is too easy. We do not need to
Mm,
like specifically mention it. I will go to the details there, like where we should modify it. So the major modification lies with the Riemannian parameterization. So here we have the scheduler of kappa t. So instead of like relying on kappa t, we just use kappa ts and our vector field just have xtxs, xtts in this way. So in other words, if if we plug in like specific scheduler, this will be like for Riemannian consistency model, this kappa t is 1 minus t. However, for the Riemannian mean flow with our Riemannian consistency model, this will be t s minus t. So we're not moving like towards directly towards 1, but towards s instead of 1. The other like theoretical deduction just still holds. We can also like achieve similar results. We already like test them on some of our data sets. They're similar, but they're more flexible. So we can define like how many steps we want to like go. So they may achieve better results on a slightly like higher number of steps, like 10 step of generation. Yep.
thank you.
Yeah, thanks for the question. Any other questions?
I have a question.
Mhm.
I noticed that you make some analysis about the matrix perspective of RCM. So I want to know, uh, does this analysis can contribute to some further improvements of your model design or loss design?
Yeah, that's a very good question. Um, so first of all, I agree with you, like the kinematics or the dynamics on the manifold does have an important impact on the final results. In our framework, these can be controlled by altering the scheduler. So you may notice that if you look at the simplified loss, there is like three different terms which involves the scheduler and their derivative. So in this way, by like alternating another like scheduler, we may obtain another like different dynamics on the manifold. So however, I want to know that each of these dynamics just like confine or are consistent with the consistency model parameterization and their losses. So yeah, I think it's worth exploring like what scheduler we try to use in our model in the future work. However, in our model, in our paper, we're just like constantly using the kappa t equals to 1 minus t, which just means we're traveling at a constant speed along the manifold. Yeah, but it is known that for some manifolds, specifically for like the protein generation, we should like use a different scheduler. For example, the free flow just use exponential scheduler for the rotation and linear scheduler for the translation. So it's definitely worth exploring if we have like a multi-model generation scenario. Yeah, does that solve your questions? Thanks. Cool. If there's no more question, I guess we can also end up early today.
Yep. Okay. Thanks for joining, and thanks for everyone for joining today. See you.
Thanks. Thanks. Mhm.